All right, today we're pulling back the curtain on one of the most critical, yet almost completely overlooked pieces of engineering in our entire world. Seriously, just think about it for a second. What's holding together the skyscrapers, the car you drive, the airplanes flying overhead, even the pressure vessels in a power plant? What invisible giant is doing all that heavy lifting? Well, the answer isn't some complicated chemical or some kind of magic. It's actually a simple, really elegant mechanical principle, a powerful clamping force that we create and harness every single day, most of the time without even thinking about it. And the master of this force is the humble bolt. But the real secret, the superpower here, isn't the piece of metal itself. It's a concept called preload. Preload is everything. It's the whole game. See, when you tighten a nut on a bolt, you're doing way more than just making it snug. You are actively stretching the bolt, loading it with tension before it even has to deal with any outside forces. And it's this internal tension that creates that powerful clamping force, holding everything together. So here's a fascinating way to think about it. A bolt is basically just an incredibly stiff spring. And the tightening process, that's like pulling that spring really, really taut. All that stored energy in the stretched spring is what provides the constant, unwavering clamp that is so absolutely vital for both safety and performance. Now, you'd probably think a bolt has its toughest job when a bridge is swaying in the wind or a plane is hitting turbulence, right? But believe it or not, its moment of greatest danger is often before it even starts doing its job. It's during assembly. As you tighten a bolt, it's actually fighting a battle on two fronts at the same time. We want tension. That's the good stuff. That's the stretch that gives us our clamping force. But to get that tension, we have to twist the nut, which introduces a second force called torsion. This combination of pulling and twisting puts the bolt's material under an absolutely immense amount of stress. And don't just take my word for it. The source material is crystal clear on this. If a bolt is going to fail from being overloaded, stretched past its breaking point, it is most likely going to happen right there on the factory floor or in the mechanic's garage, not out in the real world. So, once the bolt survives the assembly process and is properly preloaded, its work has really just begun. It now has to spend its entire life resisting a constant barrage of external forces. I mean, every single day that preloaded bolt is in a constant tug of war. It's fighting loads that want to pull the joint apart, vibrations that are trying to jiggle the nut loose, sudden shocks from impacts, and even the expansion and contraction from just heating up and cooling down. That preload has to be high enough to win every single one of these battles. So what happens when that preload isn't enough, or when the outside forces are just too much to handle? Well, bolted joints can fail, and they typically fail in one of three ways. So let's meet the villains of our story. The first failure is pretty simple. The joint just loses its grip. If the preload wasn't high enough to begin with, almost any external force can cause the parts to separate. Now, in a pressure vessel, that means a leak. In a structural joint, it means movement and, well, instability. Okay, failure number 2 is the most dramatic one. This is the sudden, catastrophic snap. It happens when the total force, that's the initial preload plus all the external loads, simply overpowers the bolt's material strength. It's a clean, sudden break. But it's this third failure mode that's the most common and, honestly, the most insidious. It's a slow death known as fatigue. This isn't about one single massive force. It's about millions of smaller, repetitive cycles of loading and unloading that slowly crack the bolt over time, often with no visible warning at all. So the really crucial question is, where does this slow death actually begin? Well, the data is incredibly specific. A whopping 65% of fatigue failures start in the very first thread that engages with the nut. So why there? It's because that spot is what engineers call a stress concentrator. Think about it like this. Any sharp corner or change in geometry, like the V-shape at the root of a screw thread, acts like a magnifying glass for stress. The forces get focused in these tiny little areas, and that's where a microscopic crack can form and begin its slow, destructive journey. But here is the good news. Engineers know these villains are out there, and they have developed an entire playbook to design joints that can withstand these forces and last for decades. And it's not just about textbook formulas either. The best engineering, as the source material points out, combines pure theory with real-world data. By studying how joints perform and, importantly, how they fail out in the field,
Engineers are constantly refining their models to make their designs safer and more accurate. And all of that feedback has led to some really clear principles for fighting fatigue. First, a high preload is your absolute best friend. It acts like a buffer, making sure the bolt itself feels very little change in stress, even when the joint is under a fluctuating load. Second, using longer, more slender bolts actually makes them more elastic, more like a spring, which helps them absorb energy. And finally, it's often way better to distribute the load across many smaller bolts rather than relying on just one big one. And this is how modern engineers tackle the problem. They don't have to guess. They use powerful software for something called finite element analysis, which lets them literally see these invisible forces and stress concentrations. They can simulate a lifetime of use in just a few hours, testing and perfecting their designs before a single physical part is ever made. So the next time you see a bolted connection, on a bridge, a building, maybe even the chair you're sitting on right now, remember the incredible, hidden engineering that's at play. That bolt isn't just sitting there. It's a highly tuned spring, stretched to the limit, silently fighting a constant battle to hold our world together. What else around you depends on this hidden, yet absolutely immense strength?